Now let us take a different approach for evaluation of a Taylor series. And this method will be faster by taking less number of multiplications. So where actually multiplications are done. So for evaluation of factorial, 4 factorial, that is multiplications are more in number, and then x power 4, then x has to be multiplied by 4 times. So there the multiplications are. So for each term we have to perform some number of multiplications. If you analyze for 4 degree 4, that is power 4, total how many multiplications are required? Let us do the analysis. For this term there is no multiplication, and here also there is no multiplication. This term x square, so x into x, so we need 1 multiplication, and this is 1 into 2, we need 1 multiplication. So total 2 multiplications are there. And here x cube, so this is x cube means x into x into x. So these are 2 multiplications, and this is 1 into 2 into 3. So these are 2 multiplications. Total 4 multiplications are there. Now x power 4 means total 3 multiplications will be required in numerator, and I'm just writing multiplications, and here 3 multiplications will be required in denominator. This is 6. So it means next term it requires 8 multiplication and 10 multiplication. So this is how we are getting the multiplication. So if I take 2 common, this is 1 plus 2 plus 3 plus 4 goes on to n terms. So this is summation of n terms. So this is n into n plus 1 by 2, this one, and the result is n into n plus 1. So if you are evaluating a Taylor series for n terms, so then total how many multiplications required? N into n plus 1 number of multiplications required. So this is nothing but order of degree of n square. So I can say that n square multiplications are required. Yes, roughly, means it's not exact, you don't have to take exact. N square is sufficient to understand that these are more in number or huge in size. So for evaluation of Taylor series by taking term by term, so for each term some multiplications are required and total multiplications are n square. Can we reduce the number of multiplication? So let us see how we can reduce the number of multiplications. Now I'll show how we can reduce multiplication. So here I can take the terms common. So let us start. I will take up to power 4. So I will rewrite that formula: 1 plus x by 1 plus x square by 1 into 2 plus x cube by 1 into 2 into 3 plus x power 4 by 1 into 2 into 3 into 4. Now in this I can take x as common for all, and denominator is 1. So this is 1 plus, when x is taken as common, so this is x by just 1 into 2. So let us just write it 2 plus x square, x is taken as common and 1 is taken as common. So this is 2 into 3, and plus x is taken as common. So x cubed by 2 into 3 into 4. So I have taken first common term. Numerator and denominator both have reduced. Now let us see if we can take more common values. 1 plus x by 1 and 1 plus, in this I can take x by 2 common. Yes, x by 2 is there. So this is x by 2, and here it is 1 plus, as x is taken, so this is just 1x and 3 plus, and here x is taken, so this is x square by 3 into 4. Then 1 plus x by 1, 1 plus x by 2, 1 plus, here I can take x by 3 common, and this will be 1 plus x by 4. So that's how by taking commons I have reduced the number of multiplications. How they are reduced? Let us see. See here there is 1 multiplication, and this term is multiplied here. So this is 1 multiplication and this is another multiplication. So 1, 2, 3. And if you consider this is multiplied by 1, so let us say 4. So only 4 multiplications are required. So if you want up to 4th term, that is degree 4, power 4, then only 4 multiplications are required. So the number of multiplications has reduced to order of n. It's not square. Earlier that was a square. So now it has reduced to order of n. So yes, by taking commons, we can reduce the number of multiplication from quadratic, that is square, to linear. We have reduced the time. Earlier it was n square. This is quadratic. So the time was quadratic. Now the time is linear. So this is faster. So one observation is by taking commons, we can reduce the number of multiplications. Now, how to write a recursive function for this approach? Now, let us write a recursive function for this. Now, let us observe this form of Taylor series and let us see how we can devise a recursive function for this one. So, first let us observe. If I call this recursively by passing x and 4, then it may be at 4, then it will call itself for 3, then 2, then 1. But if you observe, this result has to be multiplied with this one, plus 1 is added, and the result is multiplied with x by 2 and plus 1 is added, and the result is multiplied. So actually multiplication is done in this form, or actually multiplication is done in this order. First x by 4, then with x by 3, then x by 4. So, and returning time, there is nothing. If you are multiplying and adding 1, multiplying and adding 1, returning time, there is nothing. So usually the recursive functions that we have written, they were performing the operations mostly at returning time. But here at calling time itself, I should find out this term and multiply it with x by 3 and add 1. So I get this term. Then this I should multiply by x by 2 and add 1. Then I get this term. Then this result should be multiplied by x by 1 and add 1. So I get the complete result. So it means when I did for x by 4, so that I should multiply it by 1 and add 1. So actually the processing is done at calling time only. So when the first call is 4, before calling the next call, that is 4 minus 1, that is n minus 1, it should perform the multiplication. So this is happening at calling time. So this can be easily written using loop. So first let me write down how it can be done using loop, then I will show recursion. So let us write a function for loop. Integer e, integer x and integer n. Now in this I have to start from this term, right? This term. So I will take some variable for holding the result. So let us take one variable integer s, that is initially 1. Now what I have to do in each step, x by 4 multiplied by with the result s and added 1, and this becomes a result, and this is multiplied by x by 3 plus 1 and this becomes a result. So result I am taking it in s. Every time s should be multiplied by x by n, whatever the value of n is. Right now it is 4 if you start from here, then plus 1 is added and this result should be taken in s only. So this is in s. So this step I have to keep on repeating. So for how many times? For n is greater than 0 and n minus minus. That's all. So n is right now suppose 4, then it will become 3, then 2, then 1. So it will get multiplied and finally we get the result. So we can return s. So this is the step perform every time. So if n is 4, so it is performed for 4 times and the result is returned. So this is easily possible using loop. And here I have not taken any extra variable I, because whatever the value of n is, from there I am reducing. So there is no initialization part, just semicolon and the condition semicolon and n minus minus. So if n is 4, then it will become 3, then 2, then 1 and then 0. When it is 0, it will not repeat, but it will return this s. So s is having the result. Now same thing I can write using recursion, but in recursion I have to perform multiplication at a calling time. So at a calling time if I have to do, then I can take the help of static variable now. So let us write it with the help of static variable. So it will be on the same fashion. Recursive function, this is a recursive version, x and integer n. I need one static variable for storing the sum, and whose value is 1 initially, this one. Now if n is 0, means when it has reached 0, do nothing but return s. So here also I will write down s. Else, what I have to do? Else, perform this operation. So the same operation I'll perform, s assign 1 plus x by n multiplied by s. The next is as it is repeating, so here call itself again by e, x and reduce value of n, that is n minus 1. And here I should write down a statement that is return. That's all. So already we have discussed in our previous lectures that loops will have just ascending, there is no descending, but recursion will have ascending and descending. But this procedure can be performed only in ascending. So I have taken a static variable and I am storing the result in that one at calling time itself. So this is a iterative version and recursive version of a function for evaluation of Taylor series with order of n number of multiplication, that is a reduced number of multiplications. So that's all with the Taylor series. Now similarly there are more series like sine series and cos series, that is your student exercise. So you have to write down the functions. So you try to write down those functions. So here in this video we'll look at a recursive function for finding e power x, that is for Taylor series. We have already seen the procedure using Horner's rule in the previous video. That same function I will implement here. Already I have a body of a function. I will implement a function. I'll take a static double value s. While explanation I have taken it as integer, but the result is double type or decimal type. If n is equal to 0, return s. Otherwise, s is evaluated as 1 plus x divided by n into s. See, x and n both are of type integer, so I'll get integer division here. So I should typecast it as double, or else I can multiply x numerator with s beforehand so that this result becomes double, and then divided by integer also gives double. So writing statement will give a perfect result. Otherwise I have to typecast x by n. Now the next statement is return the function call x comma n minus 1. That's all. Inside the main function, I will directly print the result obtained by that function. So printf percentile lf, then slash n, call the function e1 comma 10. Let us run the program. We already know the result. Let us see whether we get same result or not. Yes, 2.718282. If I give the value as a 2, yes, it is 7.38871. Let us check it on a calculator. 2 e power x is 7.389 and we got a 388. So it is little less. If we want more precise value, then we can increase the number of terms. So that's all the implementation of Taylor series using Horner's rule.